All right, so let's see how to do this in R. All right, so we'll load some data here. So I think the idea with these data, just for some context here, they are, this is from a trial, I believe, where they are interested in, these are people who have previously had cancer, and they're interested in whose cancer is going to recur later on. And these people are being treated with this kind of like a blood transfusion treatment, and they're interested in, this is the main exposure variable, where this indicates basically how fresh the blood is that they're using to transfuse these people, and they want to know, okay, if you use fresher blood, does that prevent recurrence? Things like that. That's just a little context. So here I've loaded the data. Here's how you fit a logistic regression in R. It's very similar to the way that you do linear regression. So instead of LM, the only difference is you have to write GLM. So the G stands for generalized linear model. And it turns out you can do other things with this besides logistic regression. You can fit generalized linear models, which generalized linear models, it's just, okay, you have a line, and then you're going to wrap that in some other function. So logistic regression, we wrap that linear output in a logistic function, but there's other functions that you could use to wrap that up in. And that is effectively what a generalized linear model is. So for logistic regression, the way that you say, okay, wrap the linear output in a logistic function, you have to say family equals binomial. Okay. And by the way, GLM, you can also fit linear models if you say family equals normal here, I think. But LM is easier. Okay, so GLM, here you put your formula. This is the same as for linear regression. So here on the left of the little tilde, you put what the outcome is. So here, recurrence is the thing I want to model as my Y variable. And as my X variable, in this case, I'm just going to put age. So I'm kind of asking about how does the risk of recurrence vary with age. Then the next argument is the data. And then, like I said, lastly, this is just what tells it that you want to do logistic regression versus other things. So you shouldn't forget this. So if you run this, press enter, you can save it into an object and then print that out. And you're going to see output that looks like this, which again is very similar to what we saw for linear regression. So you get a table of coefficient values. So here the intercept is -2, and the coefficient on age is 0.008. So we can extract the coefficients if you don't want to have to manually copy them from this table. You just want to look at them. You can use the coef function, which also works for linear models. Boom, right? You can ignore this. So you can use this to make predictions. Very similar to the way that we did for linear regression. You use the predict function, and then the first argument is the model that you fit, and the next argument is the data that you want to predict on. Okay, and the difference here is that you have to do type equals response. So let me show you that. So here I can get predictions. So this is for every person in my data set. Based on their age, what's their predicted risk of recurrence? So for person 1, we have about a 17% risk. For person 4, we have a little less than that. Person 13 is maybe about 16% risk, so on and so forth. So these are the predicted probabilities of the outcome. The reason you have to put type equals response is that if you don't do that, let's just print it out like that. You get values that look like this, which are clearly not predicted probabilities. So what are these? These are the values of the linear predictor. So these values are before it's been wrapped in the logistic function. So for example, if I take, I scrolled up too far. So let's say, this last one. If I take this, and I say plogis, if you recall, that's the logistic function. Plogis of that gives me about this. And then if I take here the last value of predictions, this is the same, right? So you can see that the this, if you do type equals response, all it does is it takes the linear predictors and then it does a mutate where it applies the plogis. It just wraps that in the logistic function, and then that's what gives you the predicted probabilities. So if you want to see this, if you want to see it before it's been wrapped up, you don't need this argument. But most of the time, what you want is the predicted probabilities. So you have to type equals response, which is kind of annoying. I think that should be the default. But whatever. You can also abbreviate it, just type equals R, and that gives you the same thing, the predicted probabilities. So don't forget that. I forget it all the time. But you'll be able to tell very quickly because you're going to see these predicted probabilities that are going to be like large negative values, positive values. It doesn't make any sense. So you'll be able to tell what the error is pretty quickly most of the time. So you can see, compare that to the manual predictions, where here I have, let's say B0 is equal to coef M. Let's get that's the intercept. And then let's get the slope parameter. Right? Okay. And now we can make the predictions manually. So we take the data and we just take age times that slope and then add that to B0. So if we do that, we're going to get the equivalent of doing this without this. And then if we do it with type equals R, that's the same as just putting the plogis around that. So you can see that these are the same. Well, that's what I'm doing here. Right? So these are all basically the same numbers. And now let's have a look at this plot. So this shows us here, I'm plotting the data. So, this is a scatter plot, but it's a lot less interesting, I think, than the scatter plots where y is a continuous variable, because here y is only ever 0 or 1, so it kind of makes it hard to see actually like what if it's kind of more dense down here or more dense up there. So you can try to make it kind of these dots transparent if you want to get a better idea of that, but it's just always going to be a bit hard to see. And what I've plotted here in pink is actually this prediction function. So the actual predicted values, that's what I'm plotting there. And you can ignore this for now. I'll add that in a second. But so this is our logistic function. And why does it look flat? Well, it looks flat because we're actually just seeing a small part of this. So if you extended this, right, this would actually at some point go up, and then this kind of keeps going down, right? It's just that it's going up way over to the right. So it has found out, right, that most people actually have a relatively low risk of recurrence. So there's a lot more dots down here than there are up here. That's one thing. And then moreover, that as you move along this x-axis, the risk of recurrence doesn't appear to increase that much. It does a little bit, but not that much, right? And so it basically fit this logistic curve where the S shape is way over to the right. So in this little portion that we're seeing right here, it looks pretty flat. Oh, sorry, yeah, that was this plot up here. That's what we're looking at. Okay, so now we're going to see what happens if you add predictors. So again, this is a lot like linear regression. The first thing is the formula that you put in, and then the data, but you also have to say this family equals binomial. The only difference here is that I'm adding in this other predictor variable, which in this case is I think it has 3 levels. So it's kind of either like freshest or medium fresh or old blood. So you have this other predictor. No problem. We can do it like this. We can look at the coefficients and the output. So here you're going to have a coefficient on age, a coefficient on, since this is a factor with 3 levels, it has made dummies. So it made a dummy for group 2 and a dummy for group 3. And these each have their own coefficients as well. And you can extract those using coef. Predicting it still works the same way, right? So you just run predict type equals response or type equals R, and that will multiply these coefficients times the values in the data for these variables. Add this thing this intercept term, wrap that all in the logistic function, and then return that predicted probability. So you can see we have now these predicted probabilities, which are different than the values we were seeing before, because now we have these this additional predictor. So it's being given more information on which to base these probabilities. And here I'm going to plot those probabilities. And so I've plotted the dots. I've colored them based on the value of this other predictors. So we have two predictors, age and this thing, right? Which has values 1, 2, and 3. And then I've also plotted down here the predictions for different groups in different colors. So if you are, for example, 60 years of age and you're in group 3, your predicted risk is, let's say, about 23%. But if you're 60 years old and in group 1, then your risk is maybe like only 22% or something like that. So because this is a factor variable, we're getting like 3 different S curves, which are all, the S part is all over to the right for all of them. But we're getting these 3 different S curves for the 3 different groups. You can also do all the stuff that you would do with linear regression here. So if I want an interaction term, I can do that, no problem. So here now we have coefficients for each group and for age, and now also we have the interaction between those. And if we're going to plot them, okay, slightly different. So now when I've put the interaction in, what that does, so if you think about how, for linear regression, the interaction means that they can have different slopes, right? For the different groups can have different slopes. For logistic regression, the interaction, the slope, right, modifies, here we go. The slope changes, right? How steep the increase is and whether it's an increase or a decrease, right? And so here, because I've included an interaction, it's now allowed the risk profile for group 2 to have the kind of opposite effect as the risk profile for group 1 or group 3. And you can see that group 3 has a steeper increase in risk than group 1. Okay, so I think that's it for our little R demo. So let's do a quick problem. Let's load this COVID testing data from the medical data package. And I'd like you to use logistic regression to estimate the conditional probability of a positive COVID test given gender and age, and include an interaction between the 2 predictors. And all I want you to do here is report the coefficients and then make a plot like we had before. I was just showing you, plot the predicted probability as a function of age, and then color those lines by gender. So this is going to be very similar to what we have here. Start here. Data. Okay, so let's see what's in this data. Result is probably the outcome of the test, right? So let's just look at that. Okay, so it says negative. I think there's okay, so there's actually 3 values here. There's negative, positive, and invalid. So the problem said the probability of a positive test. So I'm going to just make a little outcome variable, and I'll just call it y. I'll just say that is equal to result being positive. There. Okay, so now I have a 0, 1 variable as the outcome. And I would like to do logistic regression there, and I want gender and age, and those things are, I probably just call gender and age. Great. So I'll just have y here. And I think it said include an interaction term, so I can include interaction and main terms just like this. There we go. And now, what do we want? Just look at the coefficients. So here's the intercept term, coefficient on gender, on age, and on this interaction. And now let's make the similar plot. get the predictions. And here we need a change. There we go. Oh, so here this is coded as true and false. So maybe I need to say, looks a little weird. Okay, there we go. So this is what the result looks like. So we can see our data, the outcomes are all ones and zeros, right? So these people with positive test, with a negative test, and it's showing the probability of having a positive test, given that somebody is the predicted probability of somebody. This is not necessarily the true probability, but it's what the model thinks of if you're check the female box on your test form and you are 50 years old, then this is your probability that that test is going to come out to be positive. Similarly for males, it's a little bit higher here. You can see that the kind of S curve is steeper for males than for females, and that is reflected here in the coefficients, I believe, for age. Yeah, so here the interaction is basically is positive, which means that we're having an additional, this is kind of like the additional slope that's being added to age for people who are male. This negative here is showing that the baseline risk for men is a bit lower. So this, you kind of see that here. This curve is actually pushed a little bit down, although it's steeper, right? So it actually ends up going up faster. And for both of these, like in the other example, the kind of S part is over to the right. We can't see it here.